Okay, so hello everyone, and once again I welcome you to this interactive session where we discuss some sample problems. So, in this session, I will solve some problems related to week 3 assignment, which starts with the Ginzburg-Landau theory basically. So, I will solve some problems related to this Ginzburg-Landau theory here. That being said, let me share my screen and okay. Uh, so, let's start with question number one. So, uh, question number one says to derive the first Ginzburg-Landau equation, okay, starting from the free energy density of the CL theory. So, we start with the order parameter of superconductivity, which is taken to be psi, that is equal to psi naught e to the power I phi. Okay, so we take the all the electrons wave function using this wave function only. Okay, so we take that all the electrons are phase locked when the sample is in a superconducting state. So every electron has a phase phi, they are phase locked, and the number density of electrons is thus expressed by this equation, where Ns is the number density and that is equal to psi star. So if you do this, you get mod psi square, mod psi naught square. Uh, okay, Govind, can you please mute yourself?
Okay, sir.
Uh, okay, so let's start with this order parameter of superconductivity, and so that is psi. And let's consider this Ginzburg-Landau free energy density, which is given by Fs, that is equal to this normal state free energy density plus some alpha into psi square. Okay, so alpha into mod psi square plus some beta into mod sin mod to the power 4. Okay, so we take basically the free energy as a function of this density of Cooper pairs. Okay, the number density. So in addition to this, okay, so by convention we take this mod of so beta by 2, and in addition to that we also consider the kinetic energy of these Cooper pairs. Okay, so that is written by so h cut square k square by 2m, as you know, but we write is in operator form. So that is given by minus I h cut delta by 2m. Okay. So this is operating on this wave function psi. So this is basically h cut square k square by 2m form. Okay. So this is in absence of any external magnetic field. So this is the free energy density, I mean energy density per unit volume, energy per unit volume, that is called the energy density. So this is the free energy density of the superconducting state, and this is the free energy density of normal metal. Okay, and we consider alpha as a temperature dependence, which is written by some A into T minus Tc. Okay, so at when T is less than Tc, then alpha is negative, and when T is greater than Tc, then alpha is positive. So we start with this. Now let's apply the magnetic field. Okay. Now let's say a magnetic field is applied on the top of the superconductor. Okay. Then the free energy. We know that in the presence of magnetic field, the momentum of these electrons, they get changed. Okay. And the new momentum hk prime is basically hk minus qa. So this is the vector potential related to the magnetic field B. So we applied an external magnetic field B, and the vector potential related to this field is A. Okay, and Q is the charge of the Cooper pairs, let's say. So Q is charge of the Cooper pairs, that is given by 2E, because we know that in a Cooper pair there are 2 electrons, so the total charge of the Cooper pairs is given by 2E. Okay, so now what we do is, so sorry, there is a little mistake, this is plus. So now what we do is we put this explicitly. So now this term h cut k, so before h cut k was minus I h cut delta psi. Now this is after applying the magnetic field, this is h cut k prime, and k prime changed as this. Okay, so now it is minus I h cut delta psi plus 2. Now in place of q we put 2e and the vector potential. So now what happens is, so the charge of the Cooper pairs is basically minus 2e. So that minus and this minus becomes negative. So to put it all once again in the place, this term ultimately becomes negative. Okay, so and we put this electron and we take the negative sign inside this only. So let's say E is equal to minus 1.6 into 10 to the power minus 19 coulomb. So we take the negative charge inside of this E, and then it remains minus only because it's the generic equation. So h cut k prime when we apply an external vector potential, it changes as h cut k minus qa. So q is the charge, and now k is the charge of the Cooper pair here, which is 2e. Inside this e we take this minus signs. Okay, so and we put this here, so it remains the minus sign. So here also we don't put the minus sign explicitly, so that is why the minus remains minus here. So it's as per your convention. Here I am taking it like this. So now if we put this whole term back into that free energy density equation, now let me put this equation back into this free energy density. Okay, so in place of this term we now put the modified term here. Okay, so it was like Fs, that is free energy density of this superconducting state, is equal to Fn, free energy density of the normal state, into alpha psi prime square, psi mod psi square plus beta psi to the power 4 plus this kinetic energy term, which is minus I h cut so this total h cut square k square goes into this. Okay, so this is now our modified free energy density equation in presence of an external magnetic field. So now we have this energy density equation in our hand, and we will start from this point basically to reach to the first Ginzburg-Landau equation. To reach to this first Ginzburg-Landau equation. Okay, so okay, let me admit this person. Now we start from this free energy density equation to reach the first Ginzburg-Landau equation. So to reach the first Ginzburg-Landau equation, first GL equation, we have to minimize this free energy density. Okay, so this is the free energy density. Now if we want the total free energy, the total free energy is then given by this volume integration of this free energy density. Okay. So this total free energy is written as total free energy of normal state plus the volume integration of this total term. Okay. So volume integration of alpha psi square plus beta psi to the 4. There is a minus sign. This is the total free energy of the superconducting state. So now we have this thing in our hand, and to get fast Zinzberg-London equation, we have to minimize this Fs, minimize with respect to psi. Okay. So we have to minimize this free energy density with respect to psi, the order parameter, to reach the first Zinzberg-London equation. Okay. So now we can expand this term. So let us simplify this equation also first. Okay. Okay. So so there will be a psi term also here, because the whole thing is operating on psi. So let's first simplify this equation. So minus I h cut delta psi minus 2 of psi. Okay, that's good. So this is basically operating on psi. The operator will take minus 2e epsilon. That is operating on psi. Okay, so this psi is not inside. Let's assume it's outside, because this is the operator, and when we write h cut k in the operator form, then h cut k square, in place of h cut k square, only the operator goes here, and the whole thing is operating on psi. Okay, so this psi will be outside here. Also this psi, the whole thing is operating on this psi. Okay. Now if we break this term out explicitly, let us break this term out explicitly. So this becomes I square minus I plus I square h cut square delta square plus 2. So this becomes 4 e square a square minus, so this becomes plus also. So this is basically I h cut. Okay, so 2I h cut, so this also become 4, 2I h cut e psi dot a. So actually let's write this term explicitly again. To do this, so first operate this thing on this. So I h cut delta a, here will be 2e plus 2e I h cut a dot. Now this term from this Maxwell's equation, we know that grad dot a is equal to 0 always. Okay. So this is the Landau gauge we take. So we consider this grad dot a is equal to 0, and then we take this. So this term vanishes basically, and so we are left with this equation: h cut square plus I square h cut square grad square plus 4. So now we have simplified this term. Now let's put this equation back into this equation. So now our Fs is equal to Fn plus alpha psi square beta psi to the power 4 and in this bracket the whole term goes here. Okay, now we are minimizing with respect to the order vector lambda. Okay, so we are equating this term to 0. So this becomes 2 a alpha 2 alpha psi. So this term is constant. I mean constant. This is not a function of psi. So this term goes 0 as we take the derivative with respect to psi. This term is 2 alpha psi plus 4 beta mod psi square psi plus, and this term, okay, so the actually is a little bit mistaken. So this derivative term is totally on this term. Okay, so we are taking derivative of this integrand and equating dash to 0. Okay, because this del psi by del f by del psi is 0 by the minimization condition, and this term when we do the derivative with respect to psi, this is 0. So obviously this term, the integrand of this term, when we take the derivative of this integrand with respect to psi, this also had to be 0. So we are basically doing that. We are taking the derivative with respect to the psi of this term and of this term and this term. Okay, so this term is inside this, so we are taking the derivative of this term also. Okay, so when we take the derivative, we are left with 1 by 4m. So this you can verify later. So this total thing is 0. Okay, so this thing implies this. Now we are taking this thing. So to take the minus sign out from here, we can write it finally in this term form. Okay. So h cut square by psi. So this minus term, so this I square basically goes to as this minus term here, and the rest of the things are same. Okay. So this term, so there will be 2 basically, because when this thing is, this is psi square, so when we are taking derivative of this psi square, it gives us 2 psi. So this is psi square when we are taking this thing out. So when we are taking the derivative of psi with respect to this gives us 2 psi. So this 2 is we are taking out from this bracket. Okay, and then we take this 2 term here, take the 2 term common from all the terms, and we are getting this form. So 2 1 by 4 pi m, we have taken the minus also common, so this minus term goes and this becomes negative. This is 0. So from here we can finally write this. So this 2 basically goes out because this is the right hand side is totally 0, and so we can keep these 2 things out from here, and thus we are reaching, now we have reached to this Ginzburg-Landau equation 1. So this is given, this is called the first GL equation. So hopefully this is clear to all of you, and if you have any question you can ask me now. So now, so what we have done is we have derived this first Ginzburg-Landau equation starting from this free energy density of the superconducting state. So we take the free energy density superconducting state expression using this Ginzburg-Landau theory. So this GL theory gives us that the free energy density is some constant Fn plus this is the free energy of normal state plus alpha amount of psi square plus beta mod of psi to the power 4 plus the kinetic energy term. Okay, so the kinetic energy term, we are keeping the kinetic energy term here, and then we are applying some external magnetic field. In the presence of this magnetic field, the kinetic energy H cut k, the momentum of the electrons or the Cooper pairs, you can say, basically change modifies to this term. This is known from this you all know from the derivation of an electron in a electromagnetic field. Okay, so if you have done the problem related to the electron's motion in an electromagnetic field, then you know this, that magnetic the momentum of an electron that modifies to this equation when we put an external magnetic field. So now we put the external magnetic modified momentum term here. In the place of q, we put the total charge of a Cooper pair, that is given by charge of 2 electron 2e, and then we put this term in back to this equation in place of this term. So because this is now modified, so by putting that in the equation, we get the final free energy density. Okay. Now if we integrate this whole term over the volume of the sample, we get the total free energy density of the sample. Okay. Total free energy, not the density, it's the total free energy. So the total free energy is then given by total free energy of the normal state plus this Ginsburg-Landau term plus the kinetic energy in the presence of magnetic field. So we then explicitly calculate this thing out, and using the Landau gauge, we put this term to 0. So now the simplified form is this, and after that we again put this term back into the equation, and by the minimization condition, we take the derivative with respect to this side, the order parameter, to be 0. So that implies that this term has to be 0. So, and from doing all the simplification, so we finally reach to this equation, which is called the first GL equation. So this ends our question number 1. Now we approach to deriving second Ginsburg-Landau equation. When we start to find this second GL equation, what we do that we take the minimization now with respect to another parameter, which is the vector potential, okay, in presence of the magnetic field. Now we take this derivative to be 0, and by calculating this, we reach to the second Ginsburg-Landau equation. Okay, so let's do this explicitly. So we have this equation in our hand. So we have this equation, and after modifying this and putting back into this, we now have the final equation like this. Okay, so the final equation can be written as Fs is equal to Fm plus so we now have this equation, the total free energy, total Ginsburg-Landau free energy of a superconductor. Okay, so this is fine, and now we have to take the derivative with respect to A. So from here we can see the A only appears here and here. Okay, so one more thing, that when we apply this external magnetic field, we also get an energy corresponding to the magnetic energy. Okay, so the magnetic energy can be written as some constant time b square. So this constant depends on which convention you are using. You are using the CGS term or SI term. In the case of CGS term, you can write this as 8 pi term, or in the case of this SI, this is written as 2 mu naught. Okay, 1 by 2 mu naught. So this C depends on which unit system you are using, but we are taking here just for simplicity that this term is C, some constant. Okay, we are just considering this term here. Now in the case in here in B also we have a, so B can be written as, so in the case of B also we have a dependence. Okay, so B can be written as this. So we also get a dependence, the vector potential dependence, through this term B square also. Okay, now when I take the derivative with respect to A, what do we get? We get 8 e square A. Okay. So we get this term. Okay, so let's do it another way. So we know that these terms are goes to 0 when we take the derivative with respect to alpha A basically. Okay, so because they are independent of A. But let's start again from this equation without simplifying the term. Okay, so from this equation, so let's start with this equation because it's now then be easy to finally reach the standard equation. Okay, so which you can see appear in the book or any other videos, etc. So then let's start from this equation only. So this term basically gives us, this 2 goes to 0. So this gives us d by dA of 1 by 2m star. Okay. So this 2m star will, this is basically 2m star, the mass of a Cooper pair. Okay. So this 2m star comes here also. Let's keep it star because it's the mass of the Cooper pair. So now in the place of m star, we know that the Cooper pair consists of 2 electrons. So m star is basically mass of 2 electron. So when we put this m star is equal to 2m, we then get the value 4m. Okay, so it's not now star. It's not star anymore. So this is the mass of electron. And here when we put it in the form 2m star, here it is the mass of Cooper pair. So these small things we have to keep in mind to get the exact solution. So whatever let's write it in this form. So we are taking the derivative with respect to this vector potential A. So now we, without breaking this term, so let's write it like this. So this implies that this is equal to 0. Okay, so we have not simplified this term only, we have kept it in its original form. Okay, so here, so if we take the minus things out, it goes out because minus square is plus. So we get the plus I h square delta plus 2ea. Okay, that we have written here. Okay. So we start from this equation and now let's simplify this. So this gives us d by dA 1 by 2m star and then minus I h cut del, because you can write this. So this is basically in a form of a square. So we know from the knowledge of quantum mechanics that if A is an operator, if A is an operator, then we can write it like A star A. Okay. So here I am writing it in that form only. So here A is basically, so to avoid the confusion, let's express it like x. Okay, so x star, because it can be confused with this vector potential. So in our case, the x star is given as I h cut delta plus 2ea of psi. So when we are writing it with in the form x star x, so we get this term because x star is minus, this I will be minus, we are taking the complex conjugate term. So this I gets to minus I and the other things remain same. this psi goes as psi star, and now we write the x, which is I h cut psi I h cut delta plus 2. So this is like this, plus this p square terms remains as it is. So this is basically 0. Okay, let's go to the next page. So this term, when we simplified it more, and this term gives us 2e. So I am just writing the simplified form. So when we take the derivative of this with respect to a, so only 2e survives. Okay, so that is why I am writing this 2e outside, and the rest of the thing is remains same as always. So, and plus minus I h cut psi star plus 2e psi. So after taking the derivative, we are getting the form like this. Into there will be so there will be 2s 2 into 2e psi. So this term is now plus d of b square by dA, that is now 0. So when we take the derivative of this term with respect to a with respect to a basically, so we get 2e psi times this thing. Okay, so that we have written here 2e psi times this thing, and plus when we take the derivative of this term with respect to alpha, then we this term with respect to alpha, a, so this then we get 2e psi star times this term. So 2e psi star times this term. Okay, so after taking the derivative with respect to a, we get this term and db square by dA. So after simplifying it more, you can write it 2e I h cut by 2m star psi star delta psi minus psi delta psi star plus 4e a. Okay, now we can prove that this term, I am writing the result only, but we can prove that this term can be written as this. So I will prove this just in a minute. So for now, let's focus on these two terms. So when we simplify these two terms here, we can see that this 2e psi star and this term and this term. Okay, so psi star delta psi and psi delta psi star goes here, and their outside terms comes here. Okay, so I h cut 2e and 2m star, and these two terms they adds up and gives us this term. Okay, and this term gives us this term. So I will now prove that d of b square by dA can be written as 2 into psi curl of a. Okay, so let's now prove this equation only. So b can be written as curl of a. Okay, then b square can be written, so this term can be then written as b square by dA can be written as d by dA of curl of a to curl of a. Okay, so curl of a, now we calculate this term. So what is d of curl of a? So d of curl of a times curl of a. What is this term basically? So this gives us 2 into curl of a to curl of dA, because when we are taking the derivative in this term, it gives us curl of a times curl of dA, and when we are taking the derivative, it also gives the same term. So these two adds up and gives us 2. Okay, now let's assume that this curl of a, let's express it as a. the vector A, and let's express this dA term. So this, let's assume this A and this dA is B. So we can then write it as this, okay? So A dot curl of B. Okay, now we know that curl of, sorry, gradient of A cross B. What is this? This is basically B dot curl of A minus A dot curl of B. Okay, so from here we get A dot curl of B. This is B dot curl of A minus A dot, sorry, grad dot divergence of basically A cross B. Okay, now we put the value of A and B in this term. So B dot curl of A minus divergence of, in the place of A we write back the original term that we have considered to be minus small a. So in the place of small a we put this term again, and in the place of B we also put back this term. Okay, now look at this term. So basically A and dA, their direction is same. So when we take the cross product of them, this term goes to 0, because we know that when the two vectors have same direction, their curl is, or their cross product is 0. So this is 0. So we get A dot curl of B is equal to B dot curl of A. So we put this here, 2 into B dot curl of A. This gives us 2 dA. We again put the value of B, or the expression of B here, dot, this is small a. We also put the expression of A here, curl of A. So what do we get? We get that this term, or basically this is d of B square. So d of B square is equal to 2 into dA into curl of A. So this implies that d of B square by dA, basically we take the dA term here. So d of B square by dA is equal to 2 into curl of A. So now we have proven that dB square by dA is equal to 2 into curl of A. So now we put the term here, and let's simplify this a little bit more. Okay, so what do we have? So dfs by dA is equal to 0. This implies this equation, 2e I h cut by 2m psi square delta psi star delta psi minus psi delta psi star. Okay. And then plus 4e this vector, this vector potential A times psi star by m star. 4e square A mod of psi square by m star, and then we put this equation also. So 2 into curl of A. Okay. Now we know that curl of A is the magnetic field B. So curl of A is equal to curl of B, and from the Maxwell's equation we know that this is equal to mu naught J, where J is the current density. So let's now put this thing back into the equation. So from here we put this total term goes as 2 mu naught j. Okay, so and also this term is 0 means this total term is 0. Okay, so we take the 2 common from each equation and just cancel it out because the right hand side is 0. Okay, so and in the place of this we can write mu naught j. Okay, so mu naught j is equal to minus I h cut e by 2m star into psi star delta psi minus psi delta psi star plus 4 a square. Sorry. Okay. Anyway, so this gives us this in. Okay, so this term is also becomes 2 and this plus sign becomes same because we are taking these two terms into the right hand side. So this is our final GL equation. So this is called the second Ginzburg-Landau equation. So this ends our discussion on the derivation of Ginzburg-Landau equation, and we will now proceed with some effect, some calculation. I mean, some what this Ginzburg-Landau equation gives us, what is the result of these equations, and how can we get the evolution of this order parameter psi and the behavior of this magnetic field B inside a superconductor. Okay, using these two Ginzburg-Landau equation, we can get the behavior of this magnetic field B and the order parameter psi, this wave function psi, how they behave inside or between a near a superconductor normal interface. Okay, we can find out their behavior. So doing that, so that being said, let's go to question number 3, and the question number 3 will be to show how the wave function psi or the order parameter, you can say also, this behaves or varies near the superconductor normal metal interface. Okay, so we will now see how using this Ginzburg-Landau equation we can show how this order parameter psi that varies near a superconductor, this superconductor, and this is the normal metal, in the interface between the normal metal and superconductor, how the psi varies here. Okay, what is the let's say the plot of psi in this region. Okay, so we'll now try to derive that. But before that, if you have any question, you can ask. Okay, so let's say we have a superconductor. A superconductor is kept in zero magnetic field. Okay, so in absence of any magnetic field, so the zero magnetic field is present now. Okay, so we have basically the vector potential is equal to 0, and we also take the region where this, okay, so in absence of any magnetic field, of course the charge density or current density inside the superconductor will be zero, because only the magnetic field induces current density in the superconductor normal interface. So when there is no magnetic field, external magnetic field, the current density J, that will also be zero. Okay. Now we know that the current density J can be written as I h cut by 2m psi star delta psi minus psi delta psi star. While this term is 0, this term is also 0. So we can write it psi star gradient of psi is equal to psi gradient of psi star. So we have this equation in our hand. Okay, and now we know that the explicit form of this order parameter psi, that is psi naught e to the power I phi. So phi is the phase vector and psi naught is the amplitude. We now put this term here. So what do we get? We get psi naught e minus I phi into e to the power I phi psi naught. Okay, so this psi naught, this is when we take the derivative of this side, this will give 2 term. Okay, and what will it give else? So from here we will get psi star is equal to psi naught e to the power minus I phi. E to the power minus I phi is now outside. Okay, if we put the value of this in this equation, it is this term. Now we take the density of state, density of these Cooper pairs throughout the sample to be constant. So, and the density of Cooper pair is written as psi naught square. So this term is constant. So this means psi is independent of space. Okay, so this is not a variable of space. So when we take the space derivative of psi naught, this goes to 0. This goes to 0. Now what do we left with then? So now we are left with so psi naught e to the power minus I psi into psi naught e to the power I psi into gradient of psi, sorry, phi, not psi, and this term is psi naught e to the power I phi into psi naught e to the power minus I phi, this term, into gradient of phi. Okay, so this is here. Okay, and when these two terms, we can, from here we can see that psi naught square gradient of psi. Okay, so here actually I think I made a mistake. So when we take the derivative of psi naught here, so we will get an extra I term, and here we will get minus I term because it's minus I phi now. So you can check it later. So for now I just write this thing minus I naught. So when we get minus I plus psi naught square delta psi minus psi naught square gradient of psi, or 2 psi naught square gradient of psi is 0. Okay. Now what does this mean? We know that the density of state, of course in a superconductor there are Cooper pairs. So this density of state psi square, not psi square or psi square, whatever you say, this cannot be 0. Okay. Because there are some finite number of Cooper pairs inside a superconductor, so this must be non-zero. So what do we left with? We left with that gradient of this phase vector psi this is 0. Okay, or we can say that the phase does not vary with the space. Okay, so this is not a variable of space, or psi is not a variable of position or function of position. Okay, now the first Dirichlet-Landau equation then gives us, so in the first Dirichlet-Landau equation, now in the, so this is our one result, equation 1. Now we start with the, what happened, anyway, I think there is some glitch happening. I have to save it. I have to again open the PowerPoint. Let's open the PowerPoint again. Okay, I think the result is not saved here. Okay, anyhow, we can do it again. So what we get is I. So we got I here and minus I here, and one second, let's save it. So this is I and minus I. So the as psi naught square, what is happening? As psi naught square, this, to take this as psi, so this gives us I psi naught square grad psi is equal to minus I psi naught square grad psi. So this total gives us 2 psi naught square grad psi is equal to 0. Now this term cannot be 0 because we know there is a finite Cooper pairs inside the superconductor. Okay, so this density of state, the density of Cooper pairs, because this is equal to this, so this cannot be 0. So we are left with the gradient of psi is 0, or this phase is not a function of position. Okay, so this is our result number 1. We can write it as equation 1, and we have also, so now we start with, so this result we have got, and now we start with first Dirichlet-Landau equation. So what did we get? So we got that h cut square from the first Dirichlet-Landau equation. We got that this term. So this is our first Dirichlet-Landau equation. Okay, gradient of psi minus 4 square psi minus alpha psi minus,
Your screen is not shared, I think.
okay, I think. Thanks. Okay. So okay, so what did we say that? We said that we show that this term is basically not 0 and this gradient of psi is 0. So when this gradient of psi is 0, we have got our result number 1. This result we will use later to prove that, to show the behavior of psi near the, basically what is the question, the behavior of wave function, how this behaves near the superconductor normal interface. So to do that we need this result. So this is our result number 1. Now we'll start with our first Dirichlet-Landau equation, and this first Dirichlet-Landau equation, in the absence of magnetic field, we put this a is equal to 0 in this equation. So what do we get by putting that? H cut square grad square psi minus alpha psi minus, so this term is 0. Okay. So this is our modified Ginzburg-Lindau equation in absence of B or A, the vector potential, because they are related. Okay. Someone is joined. Okay. So now what do we do? Now we do that. So now if we modify also, so what do we do now is you can write this as this. So this looks like a Schrodinger equation. If you notice, just this term is not familiar to us. So anyway, so this is the result we have in our hand. Now we try to solve this result to see how this psi. So basically, we will try to solve this equation for psi to get an explicit equation of psi. Okay. To do that, I will put the value. I will take that. So basically, we will take that psi is psi naught times f. Okay. So if there is a psi, because psi is a space variable function, so we take the amplitude psi naught that is independent of space. So this is not a function of space, because we notice that this term because we have to show that how this psi varies. Okay. So this psi basically varies near superconductor normal metal interface. So for that we must have to consider psi that is a function of x or some position. Okay. Now we know that we already derived that phi is not a function of space. Okay. So then we can do that. What we can do that we can write this psi as this term. Okay. Where all the space variability, well, this term contains the function of x. Okay. So where f is only the function of x and this term is not a function of x. Okay. We have separated these two terms. Okay. All the spatial dependence is now contained in this f only. So now from this Ginzburg-Lindau equation, we also know that this psi naught square is given by this beta. If we solve this free energy density that we started with, so if you minimize this term and solve this without considering this kinetic energy term, you can show that for the equilibrium position, this psi naught square must have to be alpha by beta. Okay. So when we are below Tc, when T is less than Tc. So this is the result you already know, and so and also this minus alpha term. So minus alpha is basically written as this a that I told in the beginning. So we have this results also in our hand. Okay. Now let us solve this problem, like how this psi varies. Let's say in a 1D system. Okay. So we only take the psi. We will also consider psi as a function of x only. Okay. So we are taking the 1D case. So in the 1D case, we can write this term as d by dx square. Okay. So d square. So we can write this term as dx square by dx square. Okay. So we can write down the first GL equation can then be written as minus h cut square by 4m. In the place of this grad square, we are replacing this with d square by dx square. So d square by dx square psi plus this alpha psi plus beta mod of psi square is equal to 0. So basically we have written this term only, and in the place of this we have written this thing. Now we have got this equation. Okay, and then what we have to do is we have considered this thing like psi is some function that is independent of x times some function which is dependent of x. So f is a function of x. Now we have to substitute this in this term to solve for psi. Okay. Now substituting this, we get minus h square by 4m d square f by dx square plus alpha f plus beta f cube to sin out square. Put this term there and you will see this. Or you can write it as some term. Okay, so I will not do this explicitly. So because it's some related to your assignment, so I will leave this term here. You can just simplify it and you will see that the ultimate equation comes like this. Okay, so you will ultimately get at this. You can reach at this equation where we have considered that this psi square, this is the epsilon, so this is called the coherence length. Okay, so if we put some the expression of the coherence length, you can verify this 4 pi by so if you consider this expression of this epsilon, we can get that at this equation from this equation. Okay, so do some jugglery, we do some simplification with this equation, and from this equation then you can go to directly come to this equation. Okay, and so where this size epsilon is given as this is called the coherence length. Coherence length of superconductor. So we have reached at this equation. Now to get the direct expression of psi, the explicit equation of psi, we have to find what is the expression of f. I mean, what is the explicit equation of fx? Okay. So we have to solve for this equation now. We take one more consideration of parameter. We take this x by epsilon term as eta. Okay, to simplify this equation further. Now putting x is equal to x by epsilon in this equation, we get d square f by d eta square plus f into 1 minus f square is equal to 0. Because you can take this term in the denominator and the whole term becomes like this, and in the place of x by eta, x by epsilon, you can put eta. So that is how this becomes eta. Okay. So the simplified first Ginzburg-Landau equation is this. Okay. In presence of many considerations like this parameter, of this parameter, and for a is 0. So we have taken many such assumptions, and in the presence of these assumptions, the first Ginzburg-Landau equation takes this form. Okay. Now we have to solve for this term to get the value of f or expression of as fx. Now if we put that fx in psi, we consider this psi as psi naught of fx. So if we put the explicit expression here, we can then get the explicitly how this wave function varies near the superconductor normal interface. So our next job is to solve this equation. Okay. Let's try to solve that equation. Okay. So we have this equation in our hand: d square f by d eta square plus f minus f cube. This term is 0. Let's multiply this with df by d eta. So this is again 0. This gives df by d eta into d square f by d eta square plus df by d eta into f. So we multiply this term explicitly, minus df by d eta into f cube is equal to 0. Now let's integrate this term over n. Okay, so df by dn into d square a by dn square over dn. This gives us so this gives us df by dn. So we do this by integration by part. Okay, we solve this by doing integration by part. Okay, so this gives us dn into d square a by dn square into dn minus d square a by dn square into df by dn into dn. So this is df by dn, d eta basically, and you can see that these two terms are same. Okay, so we can take these two terms in one side, df by d eta d square a by d eta square to dn, or we can write the total term. Okay, so this term is f by dn also. So what we have done is we have done the integration by part. First term is df by dn, taken integration of on this term only here. So this gives us this term, and this term gives us this term. And the second term is the derivation of first term with respect to eta, and the integration of this term with respect to delta eta into again the integration with respect to d eta. Okay. So now this term and this terms are same. Taking this in one side, we get this term, and this term gives us df by d eta whole square of it. So now we get df by d eta into d square a by d eta square of dn d eta is equal to half of df by d eta square. Okay, so now we have to put this term here again back to this equation. Okay, so this equation, from here we get that we take the integration over dn, so d square f by dn into d square f by d eta square plus df by d eta minus we are taking the integration of the left hand side only. Okay, that is equal to 0. Now we replace this term with this term. So what do we get? So we get half of df by d eta square, and now we integrate this term. So what do you get when you integrate this term over n? So so when we integrate over this term, so basically this term and this term goes out, so it is basically f df. So it's my plus f square by 2, and this term goes out, minus f to the power 4 by 4. This is equal to some constant c. Okay, now then again we have to simplify it. So df by d eta square plus f square minus f to the power 4 by 2, this is constant. So this is our final equation, simplified equation. Now we have to put the boundary conditions. So we are considering how this psi that is behaving in this region, where this is a superconductor and this is the normal metal. So this is normal metal and this is a superconductor. We want to see how this psi behaves in this region, in the interface. Okay, so to do that we have to apply the boundary conditions. So what are our boundary conditions? So let's say this is our x-axis. So we are doing it in the 1D case, so we are only considering the x-axis. So let's say this is our origin. So we know that the quadsphere exists only in the superconductor. So in the interface, this psi must have to be 0, because out of this region there should be no Cooper pairs in the normal metal. So psi is 0 means f is also 0. So f is 0 at x is equal to 0, because we know psi is equal to psi naught f. So when we keep this term is 0, because this term cannot be 0, so this is of course 0. So this is our first boundary condition. Okay, another boundary condition. What are our other boundary condition? So we know that far from this interface in this region, far inside the superconductor, the density of state in S, this is uniform. Okay, so here there should not be no fluctuation in density of state. So these uniforms mean d psi by dx is equal to 0, because psi is constant or uniform, you can say, because n is psi square. So when n is constant, the psi is constant, and when we take the derivative with respect to x, because psi is now constant, so this term is 0. And again we put in place of psi we put this term, so this gives us df by dx is equal to 0 when n is infinity. So now our boundary conditions, we have got our boundary conditions. Boundary conditions are, so our boundary conditions are df, so f is 0 at x is 0, and df by dx is 0 at x tends to infinity. Okay, so now we have to apply these two boundary conditions to this equation to solve this equation. Okay, so the equation is like this: df eta whole square plus f square minus f to the power 4 by 2, that is equal to constant c. Okay. On top of this equation we have to apply these two boundary conditions to finally get the equation of f(x). F is a function of x. Okay. So now let's say as x tends to infinity, so x tends to infinity, when x tends to infinity, so basically what we have considered, eta is equal to x by epsilon, if you remember from the previous slide. So x basically is equal to eta epsilon. So when x tends to infinity, we can also alternatively say that eta tends to infinity. So we know that at x tends to infinity or eta tends to infinity, our this term, this psi, is constant or uniform. Okay, so this is this boundary condition. Now this boundary condition can be also written as, so let's consider that it uniforms means psi is already constant, psi is not a function of x, so that this is uniform means f is also a constant, that is why df by dx is 0. So now let's the constant value of f is equal to 1. Let's take the value of f is equal to 1. So now we have the modified boundary condition as at eta tends to infinity, f is 1. With this in our hand, let's proceed to the next page. So we have this equation. The boundary condition is at eta tends to infinity, f is equal to 1. Okay, so let's put it, so let's apply the boundary condition, and f is equal to 1 means df by d eta is 0. Let's put it in this equation. So this is 0 square plus 1 minus half is equal to constant. So we now have the value of constant c is equal to half. Okay, from this equation we know the value of constant c is equal to half. So let's put back this to this equation. So df by d eta whole square so we have got this. From here we can say that d square is equal to f to the power 4 by 2 minus f square minus plus 1. So what is this? So this can be written as half into f to the power 4 minus 2f square. Okay, so the value of c is half, not 1. So this is half. So this can be written as half into plus 1 or f square minus 1 whole square. So we have got this df by deta square is equal to half of 1 minus f square whole square. Applying the second boundary condition, we have got this. So, or you can also simplify this again, equal to 1 by root 2 1 minus f square. Now if we solve, this is a very trivial this is a very trivial differential equation, so you can easily solve this, and you can see that you solving this you can get the explicit function of x. So this is, or this can be initially this can be written as eta. So if you solve this, so you can get this f eta is equal to tan hyperbolic eta by root 2. Now we put, for the case of eta we have considered eta is equal to x by epsilon or x. So if we write it here, so you can get fx that is equal to tan hyperbolic x by root 2 epsilon. Okay, so this is our final expression of f. So we have got the expression of f as a function of x. So now let's put, so we had initially psi is equal to sine of f. So putting the value of f here, we get tan hyperbolic x by root 2 epsilon. Okay, so this is how, this is the explicit behavior of psi as a function of x near superconductor normal metal junction or interface. Now if we plot this, let's plot it, so you know that how the tan hyperbolic behaves. So from, if you have read any course, done any course on magnetism, you know that the tan hyperbolic behaves like this. So from the, so tan hyperbolic of x behaves like this. Okay. So in the case of psi, so in our case, the behavior of psi also should be then like this. Psi of x. So this should be behaving like this. This value where the, this is 1. So in this value, this, because psi is given as this, when this is 1, this is psi naught. So this reaches to a value of psi naught, and this is approximately epsilon. Okay, so if you plot it, you can see that the psi is varying like this. So this is the junction, this is the normal metal, this is the superconductor. So when the in the exact junction it's 0, but as soon as we go inside the superconductor, the value of psi start to increase, and after a certain distance that is given by this epsilon, which is also called the coherence length of superconductor. So after the coherence length distance, the value of psi almost approaches psi naught, which is basically, so basically then the density of Cooper pairs reaches the value of psi naught square, which is uniform thereafter. So in this region it is totally uniform. So after a certain distance that is given by the coherence length, the value of the density of Cooper pairs, it reaches its maximum value, which is given by the mod of psi naught square. So that is how we can conclude how this psi or the wave function or the order parameter that behaves near the superconductor normal metal junction. Okay, so this concludes the answer to the question number 3. So now if you have any question you can ask, otherwise let's take a break of 1 minute. So question number 4, we will now proceed to question number 4, which will be the derivation. So derivation of London equation, which we have already derived, but from other, this time we will derive it from this Zinsberg-Landau theory, from GL theory. We will try to derive this London's equation once again. Okay, so this will be our next question. Okay, so let's start with the answer of this problem. So for this, to derive the London's equation, we will start from the second GL theory. Okay, second GL equation. So the second GL equation, as we have already derived, is given by this. And this psi, we know the form of psi is this. So now we put again the form of this psi here in this equation. So then the psi star delta psi minus psi gradient psi star, this is written as this. We already have done this, so I am just writing it here. Okay, so if you calculate this, so this term already you know that this is uniform, so this term goes to 0, this term goes to 0, and we ultimately get 2I mod of psi naught square into gradient of phi. Okay, so we had got this. Now, so putting this back in this equation, so we get that mu naught j is minus I h e by 2n 2I psi naught square okay. So this is our the form of the second Zinsberg-Landau equation. We will put this value. Okay, now we have already derived that this gradient of phi is 0 because phase is not a function of position deep inside the superconductor. We have already derived this. So putting this back into this equation, we get mu naught psi is equal to minus 2 square by mu a, or you can write that what you can write is, so j okay, So now we already know that for the Ginzburg-Landau Hamilton free energy, we can derive this for the equilibrium position. So this can be written as we have already considered that A is, so basically alpha is negative because we are below Tc, T less than Tc. So we can write this as minus mod of alpha or mod of alpha by beta. Now alpha we have considered T minus Tc. So below T, so when T is less than Tc, this is negative. That is why you can write this alpha as minus of mod alpha, which gives us this. Now let's put it explicitly in this equation. So this gives us 2 square by m mu naught into mod of alpha by beta into this, and this can be written as, so if we consider minus lambda gl square, so if we consider this lambda gl is equal to lambda gl square is equal to m mu naught by 2 square mod of psi naught square is equal to m mu naught, sorry for the interruption, 2 e square. This is the density of state. Okay, so wait a minute, just be back. Okay, so okay, so what we are doing, so we are doing this stuff. Okay, so this is the density of state, so this is the density of state and this is the psi naught square. So we can write in the place of psi naught square the density of Cooper-Fierce share. Okay, so if we consider this term as the lambda gl square, so we can put this term here and we finally get this equation which totally resembles to the London's equation. So this is called the London's equation. So now we have derived the London's equation from the second Ginzburg-Landau equation, and we have also got a second length scale. So previously we got the length scale epsilon, which is called the coherence length. Now we have got also this lambda gl, which is also called the penetration depth. We already had derived this penetration depth expression previously, but now also you can see that we have again got the London's equation. We have again also have got this exact expression of this penetration depth lambda gl from this second Lambda-Ginzburg theory or equation. Okay, so this concludes our discussion on question number 4. But before that, we can also see that how this lambda gl, that actually depends on so how this lambda gl that depends on temperature. So where does the temperature dependence comes from? The temperature dependence comes from this term, because this is given by this, and in the place of alpha we can write this as mod of A T minus Tc. Okay. So T minus Tc by beta. Okay. So mod of alpha, so this term is positive, so when you take mod of alpha, this basically becomes Tc minus T. Okay, so you can take as Tc minus T, because this term has to be positive, and when you are below T, when T is less than Tc, this only becomes positive. Okay, so the mod of alpha is given by this. Now if we put this term, so this is mod of, so this is mod of basically psi naught square. So we have now got the psi naught square and how it depends on temperature. So if we put this thing here basically, then we get that the lambda gl that varies proportionate to 1 minus T by Tc. That so T minus Tc to the power minus half. Okay. So this is how the penetration depth inside a superconductor that varies with temperature. Okay? So you just put this term exactly here. So this gives that lambda is proportional to 1 by Tc minus T, and when you do the root, it will give you 1 by root over Tc minus T, which will give you Tc minus T to the power half minus half. This is, if you take Tc outside, so this gives you T by Tc to the power minus half. So we reset this equation. So this is how the lambda so the penetration depth depends on the temperature, and how you can determine this exact behavior from this second Landau-Gilbert equation. So that's it, and then after this we will proceed to question number 5. Okay. So in question number 5 we will introduce the idea of flux quantum inside a superconductor. So the idea of flux quantum means when we take a type 2 superconductor, let's say we have taken a type 2 superconductor and we place the superconductor in a magnetic field. So in case of type 1 superconductor, this magnetic field will not penetrate, okay, this superconductor, it will bypass this superconductor like this. But if this is a type 2 superconductor, so this magnetic field penetrates through the vortices. So the small vortices of normal metal that gets generated inside the superconductor, and these vortices are normal metal, and that is why this magnetic field can exist inside this magnetic field can exist inside this normal metal or this vortices. Okay, so that is how the magnetic flux that basically appears inside a type 2 superconductor when we go beyond this HC1 or the first critical field. So if you have done the basics of superconductor, you know that in the case of a type 2 superconductor, let's say this is H. So you can see that the magnetic field, the existence of magnetic field. So if this is chi, okay, so this is M basically. So the magnetization, so this term, the chi, so that is basically del M by del H, that is 1, because you know that in the case of a superconductor this term is 1, the chi is 1. So this is 1 up to a certain particular point, that is HC1. That is because no magnetic field exists inside this region. Okay, so when H is less than HC1, there is no magnetic field that can penetrate this superconductor. That is why this chi is 1. But as soon as or minus 1 basically. So but as soon as we go beyond this HC1, some magnetic field that can penetrate and that can rise the value of M inside the superconductor. So that this magnetic field, so then this magnetization inside the superconductor goes like this, and this point is called HC2 when this is 0 basically. So at this point the superconductor is not the superconductor anymore, it's now a normal metal. All over the region of the superconductor the vortices are generated, and that is why the total superconductor becomes a normal metal at HC2. But if we consider the superconductor in this region beyond HC2 but below HC, beyond HC1 but below HC2, in this region it is now in a region where the outside is superconductor, but inside the superconductor there are some vortices is generated inside the superconductor. Okay, so now we will try to understand how much magnetic flux that these vortices can contain, or through the vortice how much magnetic flux can go. Okay, how much magnetic flux can go through this vortice, that is what we are trying to calculate. Okay, and for that let's introduce the idea of flux quantum. So we already have done this term, So this is from the second Ginzburg-Landau equation. This is minus I E h cut by 2m psi star grad psi minus psi grad psi star minus 2 e square. We already have derived this equation. Now this psi is given by psi naught e to the power I psi I phi. Putting this, we got this term. Okay. Now, whenever this there are some bodies or normal metal inside the superconductor, this phi, term, this phase factor basically is not constant or independent of position anymore. This now position of this position of this space or the this is basically a function of this position. Okay, so here this psi delta psi is not zero anymore because it's not a pure superconductor anymore. Inside the superconductor there are now some vortices that exist. So we cannot make this term is equal to 0 here. So now let's take a line integral. So let's say there is some vortice and we are taking a circular path outside this vortice. So along this path let's take the line integral. Okay. So doing this term, so multiplying both side with m by h cut e, we get okay, and minus 2e by h cut into a. So now what do we do? So we have there will be sin naught square. Now also let's divide both sides by this sin naught square and then integrate and do the line integration. Okay, so doing that we get m by h cut e mu naught j. Now we divide this by this term both sides. So now this is sin naught square. Doing the line integration along this L. So this gives us okay. So this is now our equation after doing the line integration. So now what can I do? We have to find out what is the value of this term. When we line integrate, what is this term that gives? Okay. So we know that psi is sin naught of f phi. Okay. And when we integrate this psi along a closed path, if you have done the course of Berry phase or etc., you so basically you don't have to do that course also. You can just assume that this psi, or it has to be, you don't have to assume, this psi is basically a single valued function. So there cannot be any two places. So what does this mean? So this means that at two places this value, I mean if you consider the value of psi along some point in the space, so this is a space, this is a space, at each space this psi can have only one value. It cannot have multiple value in one space. Okay, so if we take this this thing that psi is a single valued function, then that says us this phi along a closed path when we do the integration of, so this gives us basically d phi. Okay. So this term is basically d phi, So when we take the change of d phi along a closed path, this single valued function of this psi implies that this phi can only change some constant in times 2 pi along a closed path. Okay? So when this condition satisfies, then only this psi can be single valued function. Otherwise, this cannot be a single valued function. So for this to be a single valued function, this condition must satisfy. You can check or verify this later. Okay? So doing this integration, we get this. This is basically d phi, and so the phi along a closed path this change can only be some constant n times 2 pi, where n can be 0, 1, 2, 3, 1, 2, 3 basically. Okay. So this we have got. Now also know that the second term, if you come here, so the second term, so we have got the value of this term, that is 2 pi n. Now this term a dot dl, so the closed path integration of a dot dl, that can be written as b dot ds. Okay, so this term, this is basically the equation of magnetic flux. So the total magnetic flux that crosses this region, this path, this total path along this through this total path, what is the value of magnetic flux that can cross? Okay, so that magnetic flux can be given by this b dot ds. This you already know from electromagnetism, so we can write it as psi. This is the magnetic flux. Okay. So now we just substitute these two terms there in the main equation, and you can get, by substituting these two terms, you can get that okay. So we have put the value of this term to be phi and taken this term in this side, and this is 2 pi n. Okay, so we have multiplied both these two sides by h cut by 2e. So we have multiplied this term by h cut by 2e. So this goes out, and this gives us h cut by 2e times 2 pi n. Okay, and by taking this term this side, we get it plus phi. When this term comes here, this becomes plus phi. So now we finally get this equation. Now what is the implication? So let's write the equation once again. We have got that this is this. So this is our final equation that we have in our hand. So now we can show this term. This is called the flux quantum. So we can see that from here. So the total magnetic flux that can pass through the sample is some constant n times the flux quantum phi naught, where phi naught is given by h by 2e. Okay, so this is our final equation. So this phi naught, you can calculate the value of this. So this is 2.07 to the 7 Gauss centimeter square. Okay, so this is very small, and so this is basically what is the significance of phi naught. So let's try to understand what is the significance of phi naught. So basically we considered a vortex inside a superconductor. Now we calculated this equation in this line integral along a path outside the vortex. Now we know that the magnetic field only can exist inside the vortex because it is the normal matter only. Outside it is a superconductor. So here there can be no magnetic field. So the magnetic current density here can be 0, is 0 basically. So J is 0 here. And if we put J is 0 here, what do we get? This phi is equal to h cut by 2e in or is equal to n phi naught. So this says that this is the magnetic flux. So this says that the value of the magnetic flux that can pass through a Cooper pair, or sorry, the value of the magnetic flux that can pass a vortice inside a superconductor is only a constant number in times this value psi naught. Okay, so the magnetic flux value, the magnetic flux that flows through a vortice inside superconductor is constant times phi naught. So we can see that the magnetic flux that can flow through a vortice is not continuous anymore. You cannot pass the arbitrary amount of flux through these vortices inside a superconductor. So now the flux that can pass through these vortices inside a superconductor, they are basically quantized. They can be either phi naught or 2 phi naught or 3 phi naught. They cannot be like some 3.1 to 3 phi naught. So they are not continuous. So they are now quantized. Okay? So that is why this phi naught is called the flux quantum. Okay, so any kind of vortice you can find inside a superconductor, the flux that is passing through this vortice, if you measure that, it will always be a constant times this phi naught. Okay, so it's always be a, some integer multiple of phi naught. That is what this phi naught or flux quantum signifies. Okay, so also by measuring this phi naught, you can verify that when so in general inside a superconductor, when it's in the ground state, then this n is basically 1 in general. Okay, unless the superconductor is in an excited state, this n is always 1. So when we measure this flux quantum, when you measure the how much magnetic flux that is passing through a vortice, so by measuring that you can measure the value of h by 2e. So from here you can verify the value of the ratio of two natural constant. We know that this is the Planck's constant and this is the charge of electrons, and these are two natural constant. So these are everywhere the value of h and e, they are same always. So this is the natural physical constant, and by measuring the magnetic flux that is passing through a superconductor vortice, you can verify that the ratio of this h cut by 2e that we claim, or that is universally told, that is exactly close to this flux quantum value. Okay, so if by doing a measurement of measuring this flux quantum phi naught, so you take the value of h cut here and by 2 into electron value here. So this is the ratio of this, and now if you do the measurement of a superconductor and if you try to measure the magnetic flux that is flowing through a vortice, you can verify that the magnetic flux that is passing through the superconductor is very close to this value. Okay, by that you can verify that the universal constant, the value of the universal constant that are proposed or that are generally used, they are exactly matching. Okay, so this is a very important aspect of measuring the superconducting flux. Okay, so this ends my discussion on this flux quantum. So there's not much time left, so briefly I will discuss or go to our next question, that is question number 5. Okay, sorry. So let's just try to briefly discuss on question number 5. Sorry, this is question number 6. So the question number 6 is how do we can get the modified London's equation from second Ching-Landau theory. Let's try to answer this. Okay, so we have already done most of the things related to this. So what did I get? So we did get that. So we got in our previous calculation that this is the line integration expression. Okay. Okay, so now if you put the value, so if you take this term out, so m by 2 is square so this term is basically 1 by lambda GL square, the presentation text. So I reach to this equation. Okay. Now what do we do? We know that this j, so this term, this j dot dl, it can also be written as curl of j dot ds using Stokes law. So using so yeah, so using Stokes theorem, we can write this term as this. Okay, and also we know that the curl of j, sorry, so we also know that this curl of b, that is mu naught j, or j is equal to 1 by mu naught into curl of b. Put it here, so what do we get? J dot dl is equal to 1 by mu naught curl of b dot ds. So by taking it out here, so mu is absorbed in this lambda gl. So what do we get then? So lambda, okay, so this is not 1 by lambda gl square, this will be in the upside. So this is lambda, so what do we get? This is lambda gl square into curl of b dot ds plus phi. So phi is magnetic flux, so this is b dot ds is equal to n phi naught, or lambda gl square into curl of b plus b. This whole terms goes to the area integration. This is our n phi naught. Okay. Now in general, as we already said, that n is equal to 1 for ground state of a superconductor, so this can be written as psi naught. So now to write it as a surface integration, we can just write it as this. Okay, so when we take the derivative, so when we take the surface integration of this Dirac delta function, so it always gives us 1, as we know, if the area surface includes the origin, r is equal to 0. So we can write the 1 as this. Okay, so this can be written as psi naught times 1, and the 1 can be written as this. Now, so then the integrand of both these terms, so both has the area integration. So now the integrand of this both term then has to be similar or same. Okay, so this terms implies that curl of b plus b is equal to, so we have now equated the integrand. Okay, so this is our final equation, or we can further modify it and say that minus, so we know that grad of b is equal to minus grad square b. So I have derived it in the last, I think the last session only. So you can use this result and modify this term as grad square b plus b is equal to or this is called the modified London equation. Why this is called the modified London equation? You see that in the case of London equation, what do we get? Grad square b is equal to b by lambda square. So in the case of just normal London equation, it gives us minus b is equal to 0. So from the normal London equation, with this gives this. Now we see that the difference between this and this only, that the right hand side is not 0 anymore. So whenever there is a vortex inside a superconductor, so in a pure superconductor, there is no such vortex. So there cannot be no such flux quanta inside the superconductor. So this is purely 0 inside a type 1 superconductor, in which there can be no presence of vortices. But in type 2 superconductor, above the first critical field or the lower critical field, you can say, there is some vortices now inside the superconductor. So there can always exist some vortices or some flux, magnetic flux inside these vortices. So that is why this right hand side is not 0 anymore. It is replaced by this term, which is given by the flux quantum times the Dirac delta function. It basically denotes what the vortices are present inside the sample. Okay. So this is called our modified London's equation. Okay, so this concludes the question number, the discussion on question number 6, and so this is how much we have discussed, and so I'll stop the discussion session here because there is not much time left. So basically, what I have derived is the modified London equation. Okay, so this term can be written clearly as this. Okay, so this concludes the discussion.